Okay. Last class. Last chance for statics.
How much of today will be on the test?
Well, all the friction is going to be on the test.
Okay.
So we have 3 more friction things, but the good news is there are only a total of 4 friction problems. You already did one of them. They're not particularly hard, I don't think, and the questions that will be on the exam will be a lot like those questions. So you should have plenty of time to study other stuff. Okay, so the first thing is, here are the options that I can offer you for the final. The first one is take the test in class tomorrow. This is the default option. If you don't tell me otherwise, this is the one I'm going to assume you're going to do. In class Thursday. Then you can also take it in the testing center Thursday. That lets you take it a little bit later. It's open from 1 to 7 p.m. So you need to start taking it by about 5. It's a 2-hour exam. Then the third one is you can take it tomorrow. No, tomorrow is Thursday. You can take it Friday in S1328. That would be with in Tony Weinbeck's class. I'm not sure what class it is, but and those hours are different. That would be from 10 a.m. to noon. And then the fourth option is you can take it next week in the testing center. So that's 1 to 7 p.m. Monday through Thursday. That's not a 6-hour exam. That's the hours that the testing center is open, if that makes it seem any more appealing. What? Oh, Monday is the 4th, isn't it? So that would be Tuesday.
One funny question.
Mm-hmm.
For the person who takes tests tomorrow, does it get extra credits?
Possibly like sort of intangible, like emotional extra credit, you know? It makes my life a little easier, so that's probably worth something. Like karma type extra credit.
If we're thinking about doing it like Friday or this week, but then we change our mind on Thursday and the class, it's still okay.
Yeah, sure. Yep. So if you're going to do 2, 3, or 4, please let me know which one so I know how many tests to put in all these places. If you're going to do 1, you don't have to talk to me about it. I'll just assume that that's what you're doing if I don't hear otherwise. Any questions about that? The tests? Yeah, essentially the same. Probably slightly different versions. Okay. So that's it. Talk to me if you're going to do any of 2, 3, or 4. And then, bless you, exam 5 topics are everything, including friction. So we have to finish that today. That's, and I think that's it. Okay. Anybody have any questions before I get back into friction calculations? Questions about homework or anything like that?
So you know how you said if you do better on this exam, your lowest gets dropped?
Yeah, not dropped, but replaced. Yep.
So if you do worse on this exam than your other lowest one, well,
No,
it work the other way?
it doesn't. That's a good question, but no.
Okay.
So this one counts no matter what, because it's the only like full cumulative test on the class. Any other questions? Okay, so last time we talked about square threaded screws. So going back to friction. The topics are square threaded screws, belt friction, and bearing friction. And bearing friction is broken up into journal bearings and thrust bearings. We're done with this one, so the next one is belt friction. Okay, so what's belt friction? You know how Rapunzel, like when she's up in her tower, okay, here's Rapunzel. She's got really long hair. I don't know if you've heard of her before, but this prince wants to come up and play Nintendo or whatever. So she sends her hair down to let him come up, but obviously it would hurt a lot to just have someone hanging off your hair. He's not like the thinnest guy. So she like wraps her hair a whole bunch of times around this pole in her window and then drops it down. And then the prince can climb up the Okay. It still probably hurts. Okay, so she's taking advantage of belt friction. If you wrap a cable around an object, there's a different tension on the two sides of where it's wrapped. There's a high tension on this side and a low tension on this side. And so for the calculation, if this is and we're always doing this with the cables wrapped around a circular object. So if this is the thing the belt or the cable is wrapped around, here's one side of the cable, here's the other side of the cable. there's a T1 on one side and a T2 on the other side. We'll always assume this is the high tension. And this is the relatively lower tension. And if you draw lines from the center of the object out to where the cables leave the object, you can think of the amount of wrapping that's being done as represented by this angle beta. This has to be in radians. I'm not going to go through the derivation, although it is kind of, the derivation does follow a set of steps that you see a lot in mechanics, but it's kind of tedious and I don't know, it takes a while. So I'm just going to try to show the thought process of the derivation. So it uses the isolation of an infinitesimal piece of the cable. And so this infinitesimal piece of the cable I'm going to represent this way. It has some radius of curvature because it's being wrapped around this circular object. And if you think of the loads, so this is the free body diagram. If you think of the loads acting on this piece of the cable, there's a tension acting on one side. Over on the other side, there's a slightly different tension, not there's not a finite difference between the tension on this side and the tension on this side because this is infinitesimally small, but there's this small increment of tension that changes over here. There's a normal force acting. There is a friction force acting, and if we think of this as being the higher tension, then what that friction is doing is fighting this from sliding to the right. So that means that the friction force has to be this way, perpendicular to the normal force. And that is a magnitude of, actually, this normal force is also not finite because we're just talking about, so this normal force is really a distributed load that's distributed over the whole cable. So this really should be an infinitesimal piece of the normal. And that means that this friction force is the coefficient times that infinitesimal normal. And there's this small angle change. You can think of this angle as being d theta over 2, and this is d theta over 2. We're just splitting up that angle into two pieces. And now Newton's second law lets you, if you say that this is in equilibrium, Newton's second law lets you add up all these forces, do the trigonometry, and you end up with a differential equation. An ordinary differential equation. And the solution to that ordinary differential equation is an exponential function. any of you who've talked about or had classes where you talked about ordinary differential equations, exponentials are often a solution type. So it gives a solution that's an exponential, and that's not too surprising or unusual. And so the final form is the ratio of T2 over T1 is equal to E to the power of the coefficient times that angle beta. All right, so what are the ranges of possible values that this exponential can take? Well, what's the lower bound? It could not be wrapped at all, right? Or touching at just a single point. In that case, what would beta be? 0. And so you'd have e to the power of 0, which is 1. And that means that if that cable isn't wrapped at all over the object, T2 and T1 are the same. Okay? And then as you wrap it more, it can, this ratio can go all the way, it can tend towards infinity as it's wrapped more. Okay?
So as it's wrapped more, E gets smaller, is that what you're saying?
As it's wrapped more, beta gets bigger, and so e to the mu beta gets bigger. And so the more you wrap it, the bigger the difference is between the tension on one side and the tension on the other side. And so what that says is, how many times does Rapunzel want to wrap her hair around this to make it less painful? She wants to wrap it as many times as she has hair, because the more she wraps it, every time it goes around, that's 2 pi. You're adding 2 pi to beta, and you're increasing the ratio of the tension on the print side to the tension on the head side.
But then if you had the thing that you're wrapping around, doesn't that come into the equation? If you have something that has more friction, there's more.
That's the mu. So mu represents the coefficient of friction between the object and the cable.
Oh, okay.
So yeah, if it's the higher the coefficient of friction is between those two, the bigger the difference in tension is on the two sides. Anyone have any questions about the sort of the basic idea? Yep.
Does it ever reach like a critical number of times wrapped?
This says no, but in mathematically, I don't know. Probably, but I don't know. This says that it just tends towards infinity as you keep wrapping it.
So you said that the higher mu is, the larger the difference between the two tensions are?
Yep.
And that kind of seems counterintuitive to me, because if the thing that you're wrapping around has more friction, then how is it that one side is going to be able to essentially pull more or kind of carry more force
Yeah.
relative to another side?
Well, think of it. If there's no friction between the two, you can think of it as like think about it as wrapping the cable around a pulley. Okay? So what happens if you wrap this cable around a pulley 50 times? A frictionless pulley, we'll say, is an idealization. If there's a tension T on this side, what's the tension on this side? It's T. It doesn't matter how many times you wrap it because the pulley doesn't have any friction. On the other hand, if this wasn't a pulley, if this belt was made out of rubber and this was fixed, I don't know how to represent that in a drawing really, but imagine that now you kept this pulley from rotating, okay? And rubber and metal have a high coefficient of friction, and you wrapped it around 50 times. And you apply a tension T to this side of the pulley, how much of that tension is going to be felt on the other side of the cable? Like none. That's the idea, yeah. Okay, so let's do an example. Any other questions?
Yeah. According to the beta, you said it has to be in radians and it equals the number of times wrapped.
Well, in the drawing that I did, it's not wrapped even one time around, so beta would just be the angle between the two places where it leaves. But if it's wrapped a full time around, that would be 2 pi. If it's wrapped a full time around plus pi over 6, then it would be whatever that fraction adds up to.
So
It's impossible.
if you wrapped it around 3 full times, it wouldn't just be 0.
That's right, it would be 6 pi.
6 pi.
Right. Yep. Okay, so let's say that this is the object. It's not a pulley, it's fixed. That's important because if this is a pulley, none of this stuff has any effect on anything. And let's say that over here, you have a 100 kilogram mass. And over here, you're applying a force F. What F is required to maintain equilibrium if first the cable just goes, over the top and then leaves on the other side? So let's say the cable isn't wrapped multiple times. And second, what if the cable is wrapped 3 times before leaving the object in the configuration that's shown there? So before losing contact with the object. Okay, so for part A, what would be the angle beta? Oh, and I need to give a coefficient of friction. Let's say the coefficient of static friction is equal to 0.4. So for part A, the cable's in contact starting at this point. It's in contact all the way over the top until it gets to this point, and then it leaves. What's beta equal to? Pi. And so T2 over T1 is equal to e to the power of 0.4 pi. So we have T2 is equal to 981 newtons. So 981 over T1 is equal to e to the 0.4 pi. So T1 is equal to 981 over e to the 0.4 pi. So what do you get for that? I don't have that calculated. 0.4 is the coefficient of friction that I gave. What is it?
79.
Okay, 279.2 newtons. Okay, so in order to support this 100 kilogram mass, it's a considerably smaller force that you have to apply over on the other side. Now, what do we expect to happen if you wrap it 3 times around? Is F going to get bigger or smaller? Smaller. What's beta equal to if you wrap it 3 times around and then it leaves? 7 pi, so it's going to be, it's 6 pi for the 3 wraps, and then you're back here, and then 1 more pi to get over the other side. So beta is equal to 7 pi. So 981 over T1 is equal to E to the power of 0.4 times 7 pi. So T1 is equal to 981 divided by E to the, what's that, 2.8 pi. What do you get for that? 0.1? 0.148 newtons. So it's tiny, and so your question about is there like a cutoff where there's basically no force? Like, you'd probably say that we've already reached it by now.
Shouldn't have a 6 pi instead of 7?
It's because we went 2 pi there, 4 pi, 6 pi, and then 1 more to get to the point where it leaves.
Question.
Yep.
So, why the T2 have to be the weight force rather than the other side pulling force?
Other than what?
Other side, the pulling force. Why does the T2 have to be weight force?
T2 always has to be the bigger force.
But how do you know F will always smaller than the weight force?
Well, there's always going to be one force that's required to keep it in equilibrium, and one force that's like a given force. In this case, the given force that you're trying to keep in equilibrium comes from that 100 kilogram. You can think of this F as like a reaction force.
I have a quick question. Where did you get that 7 pi from? I understand if you go around the circle 1 time, you have 2 pi.
Yep. So 3 times is 6 pi.
Pi, and then, so where is that?
Okay, so 6 pi, this is where it touches the object, right? Then you go 6 pi, and you're back to this red dot. And then it's another 1 pi to get over here to where the cable leaves contact with the object. Yep.
So would it be safe to say like a 3-inch revolution is almost an integer, where you're almost adding that amount?
Yes. Yes. Yeah, each time around you're just adding 2 pi. Right. Any other questions? Okay, so now bearings. There are 2 types that we're going to talk about. One is journal bearings. And I think the easiest way to think about this, the difference between these two, is what part of the joint, or what part of the 2 sides of the joint are in contact with each other. So a journal bearing is like the way I've been drawing pin joints. Let's see. Okay, so if this object is rotating in this like pin joint in this bearing, the surface that's in contact is like the underside of that pin in contact with the bottom of that hole. Okay? You see that? Somehow in my mind I thought I was going to be able to draw this more clearly than that. Okay, so this is the place where it's in contact. That's a journal bearing. A thrust bearing is like you have this axle in contact with a wall or a floor or something, and the surface that's in contact is where the obscured side of that axle makes contact with the wall. Okay, it's called a thrust bearing, so this is the contact, because that friction comes from thrust applied this way. Okay, so yes? This is like that's like, it's like this. That's a thrust bearing. The friction rubbing like this. A journal bearing is like the friction in a motion like this.
So it's kind of like when they connect shafts for like drills or shafts
Yeah.
for propeller. They're connected to another flat surface and then turning with
Yes,
thrust.
that's right. Yep, that's right. Like any kind of clutch. I assume that's like a clutch mechanism, right? Any other questions about those? All right, well, let's do a journal bearing.
Wait, can I ask
Yeah.
a question? How come the contact for the one on top, the journal bearing, isn't the entire, like all the way around?
Actually, you're right. It does make contact all the way around, but if you, it's a distributed load all the way around. That's a really good point. But if you calculated the point where that distributed load acts, it's down towards the bottom. But you're right, it does make contact all the way around. And actually, where that idea of going from a distributed load to a point where that force is applied is going to be a key to understanding how this calculation works. It's a region, but you can always find a center of pressure, it's called, so you can always find a point where that distributed load would act if it were a point that makes it an equipolant system. Yeah, right. Okay, so journal bearings. So this is the bearing. And there's an axle extending on both sides. And you can think of this as rotating this way. And let's say that there's a weight applied to the axle. And it's split over the two sides, so we'll say that half of the weight is applied over here, and half of the weight is applied over here. And we'll think about observing it from the side. And we're going to isolate the axle. Yeah. It's supposed to be like some dumb hillbilly hick. What's an axle? Like that. What's an axle? I took statics at Century. No, just kidding. All right. So there's the axle, side view, like this guy sees. There's going to be a weight acting this way. And let's say that the thing is rotating this way. Okay, well, first of all, if this is in static equilibrium, there's going to be an equal and opposite force acting from the bottom, right? There has to be, or else it would be, the center of mass would be accelerating. If there's no angular velocity, then that W would be acting right at the bottom. And like you said, there's actually a distributed load around the whole boundary. But if you found the center of pressure, if you found the point where you could treat that distributed load as a point force, it would be acting right up from the bottom. But now if we add an angular velocity, what you get if you measure that center of pressure is you get a W acting from the bottom in a place that's not right at the bottom. And because of that offset, if you think of this as a distance rho, in order to keep this rotating with a constant angular velocity, you need to apply a couple to this object that's equal to W times rho. Okay, this W times rho is a moment that friction is applying that's slowing this down, trying to stop it. Okay. Yes. So imagine, okay, so this is a complete free body diagram. Think of the rotational Newton's second law, and as the about point, let's take the center. Okay. There's no moment produced by the W from the top, because it's acting right through the about point. Okay, but there is a moment produced by the W from the bottom, and that's equal to, it has a moment arm of rho, a force of W, and it would cause a counterclockwise rotation in this case, so that's positive. And so in order to keep this going with a constant angular velocity, if we're going to have no angular acceleration, we need to add some couple to it. So m is equal to negative W rho, and that's required to prevent an angular acceleration.
When you say angular acceleration, where would it be accelerating?
The angular acceleration means it would be, the rotation would be speeding up or slowing down if we didn't apply an external couple of m to counteract this w times rho. Yep,
So this is without angular velocity or with?
with angular velocity. So, in other words, when the axle's rotating, there's a moment of w times rho trying to slow down the rotation, stop the rotation of the axle. Okay, so if we want to figure out the couple that we need to apply to keep this rotating with a constant angular velocity, we need to come up with an expression for rho in terms of coefficients of friction, that kind of thing.
Can you maybe just quickly go over the different W's on that diagram? Because there's one
Yeah.
that's kind of rotating. So is that
W is the weight.
Yes.
This omega is the angular velocity, so that's just saying that it's rotating.
The W on the bottom is the friction.
The W on the bottom is the same as the W on the top. That's just, we know that whatever weight's applied to the top of the axle, the bearing is applying to the bottom of the axle.
It's like a normal force.
Right. But the fact that it's offset from the center is why we have this moment that's trying to slow the rotation down. Okay, so any other questions? So blow up the, I'm just going to zoom in on the axle, and let's think about what we know. Okay, so there's the axle, there's the center. We have W acting down. We have W acting up somewhere over here. And actually, I'm going to make that a little longer. Okay, so that's W. And if we knew the angle between where W is acting and that line from the center, if we knew that angle theta, we could figure out what the moment is, because this is the rho that we want. This distance is the radius of the axle, which is easy to measure. Yep.
Why is that just friction force
The W? Yeah, that's the next thing we're going to do, is we're going to break up that W into a normal force and a friction force. Okay, so notice now that this W that's a contact force. And so you can break up that contact force into a normal and a friction. where these two are perpendicular. This is the normal force. And the friction force is equal to the coefficient of friction times the normal. And the helpful thing about this, like, why are we talking about this stuff? We don't want to know anything about this. We just want to know that angle theta, right? But the great thing is that this angle is the same as the angle theta that we want. So since those thetas are the same, we can use that, I'll call this the load triangle or the force triangle. Use the triangle of forces to find that angle theta. Yeah, we're going to, this triangle here, we don't have any need for any of that stuff except that this is going to let us solve that angle theta.
Yeah, I'm just clearing up what you mean by the triangle of forces.
Oh yeah,
So know what
I
you
mean this one. Okay, so let me draw it down here. So this is the angle theta. That's 90 degrees. This is mu sub n. This is n. And so theta is equal to the inverse tangent of mu n over n. And those n's cancel, so theta is just equal to the inverse tangent of mu.
Would you typically know the normal force exactly, or you?
No, but you don't even need to. What you know is that W.
They just need to wait, and then you can figure
Yeah, from the, you see the normal canceled out anyways. So you know that coefficient of friction and you know the weight.
So you just need to know that the coefficient of friction.
That's right. That's all you need. Yep. Because they cancel out here.
So what do you need the rho vector for?
Okay, so the rho vector, now that we have this theta, the moment that you need to keep this rotating is equal to rho times W. And rho is equal to r times the sine of theta from that other triangle. So r times sine theta times W, you can rewrite that as r times the sine of the inverse tangent of mu times W. And what's the sine of the inverse tangent of mu? So this is a correct answer. This tells us the moment. But we can simplify this a little bit if we want. And in engineering, it's not really that necessary to simplify stuff. But we can simplify the expression for m if we think of a triangle with an angle theta that has an inverse tangent, or sorry, that has a tangent that's equal to mu. Okay, so the simplest triangle that you can have that has a tangent equal to mu, since tangent is opposite over adjacent, has mu over here, and 1 over here. And then, so what's the hypotenuse of this right triangle? Wrong. It's 1 plus mu squared square root. Your answer of nothing was wrong. Okay, so then what's the sine of theta is mu over 1 plus mu squared square root. And so the final answer is that m is equal to mu times r times w over square root of 1 plus mu squared. So that's the moment required to keep the axle rotating with a constant angular velocity. Okay, so let me do an example. Any questions? Any more questions before I do this? Yeah. Really?
I've been drinking a lot of fluids.
Okay, yeah. Okay, let's take a break, and I'll do an example, and I'll do the other type when we get back. So what's that? 208. Okay. So here's an example problem. The idea with these example problems is I just want you to go through the same steps of that derivation, except you can fill numbers in as you go if you want to avoid having all the variables hanging around. Okay, so let's say that we have a 4,000 Newton load there, a 4,000 Newton load there, an 8,000 Newton load there. The radius of this axle is 0.03 meters. So like if you used calipers to measure the diameter of this, that would be 6 centimeters. And the question is, what's the couple M that must be applied to this axle to maintain constant angular velocity? And let's say that these surfaces have a static coefficient of friction of 0.05 and a kinetic coefficient of friction of 0.02. Okay, so we'll go to that free body diagram. this problem is happening upside down. How's that going to affect this problem? Not in the least. You can still draw it however you want it. We're just looking for scalar values. We're not worried about directions. So, but what is once we calculate this moment m, what direction would you have to apply that couple to keep it rotating with a constant angular velocity? You have to apply it in the same direction that it's rolling, because that friction is trying to slow it down. Okay. Okay, so we have a force of 8,000 acting down. Those are the two 4,000 Newton forces that in the drawing are really acting in the other direction, but we don't care. And then over here we have the normal force and the friction force, and those add up to 8,000 here. This is N. Oh, now we have to think about, so this leg is mu times N. Which mu do we want? Kinetic, because we're talking about it already rolling and we want to keep it rolling. If the question asked what moment you have to apply to start it moving, then you'd use the static coefficient. So this is 0.02 N. And so we're trying to find this angle theta. That's the same as this one. So this is 0.02 N. This is N. Theta is equal to the inverse tangent of 0.02 N over N. Cancel the N's, and you get inverse tangent of 0.02. And if you want to just calculate that numerically, you can. You get an angle of about 1.15 degrees. So in my picture, it's way exaggerated.
Where did you get 0.02 from?
That's the coefficient of kinetic friction that I gave.
So in here, we can use the degree, right?
Yep,
Use the previous one, we have to use beta 1.
that's right. This degrees or radians are fine in this one. You're just trying to find that angle.
Okay.
Yep,
So it's already moving, that's why we use the unit kinetic.
that's right.
Okay.
Yep, to maintain a constant angular velocity, so it's already moving. Yep, but if it says it's at rest and you're trying to see what moment you have to apply to get it moving, then you use the other one. Okay, so then rho is equal to, so this is rho. This is r. So rho is equal to r times the sine of theta which is 0.03 times the sine of 1.15 degrees, or 6.0 times 10 to the minus 4th meters. And then the moment is equal to rho times the weight, which is 6.0 times 10 to the minus 4th times 8,000. And you get about 4.8 Newton meters.
And the reason it's 8,000 because that's the 8,000 is keeping it at equilibrium, so the weight has to.
Yeah, it's because if you look at that original picture, there's 8,000 newtons applied down to the axle and 8,000 newtons applied up to the axle.
So is that the 4,000 on both ends, or is it that 8,000?
Yeah, both of those two 4,000s add up to the 8,000 down, and then there's also an 8,000 up.
So are you saying you can put either of those?
Either of what?
Either 8,000 you can
The
put?
four, two 4,000s equal the offset.
Yeah.
Right. Yeah. We really drew this upside down from what's happening, but you just have to figure out what the, just add up all the forces acting on the axle itself, and that's W. Okay, this is something, I didn't say this yet explicitly, but what kind of lubrication works? So we're talking about very small coefficients of friction, a very small moment to keep this rolling, which is good, you know, because otherwise it's damaging your axle all the time. So obviously there's some kind of lubrication. What kind of lubrication works for these calculations? Yeah. That was not the answer I was going to give. Well, remember that all of these calculations are based on treating friction like it's equal to the coefficient times the normal. And that only applies for dry friction. So this is not applicable to cases where you have like a wet lubrication, where you have like oil. This is only applicable to dry lubes like graphite or whatever. Okay, you'd have to use a different approach if this is using a large amount of oil, because with a liquid, that friction force is proportional to the velocity, not proportional to the normal force. Okay. So all of this friction stuff applies for dry lubes only. Okay, so now let's do the last kind. Thrust-bearing friction. And what we're talking about here is let's do this for a, just to make it a little more general, I'm going to do this calculation for like a hollow tube. But there's a total force P applied that's pushing this hollow tube into the ground. And this tube is rotating. And there's a friction force between the contact at the ground with the bottom edge of the, or the bottom surface of this cylinder. So what's the couple that's needed to keep this rotating with a constant angular velocity? Okay, so we're going to look at that surface of contact. There's the outer radius. There's the inner radius. So I'll call this capital R inner, and I'll call this capital R outer. And we're trying to figure out, so as this thing rotates around, every point in contact is going to have an associated normal force. Well, it's actually going to be an infinitesimal increment of normal force. And because of that normal force, it's going to have an associated friction force. And that friction force is going to produce a moment. And that's where the moment's going to come from. The problem is that each one of these points, so that has a certain normal force, that has a certain normal force, all of these have these normal force dNs, these infinitesimal normal forces. But based on the moment arm between these and the center of the cylinder, each one of these normal forces, the friction force corresponding to each one of these normal forces, is going to produce a different increment of moment. So we need a way to do, we're going to do this as an integral problem. So we're going to choose an increment, infinitesimal area of contact. I'm going to spend the rest of class just filling this in. This has a thickness of dr. And from the center out to this thing, we'll call that lowercase r. And we're going to figure out what the moment applied by all the friction on this infinitesimal ring is, and then we're going to integrate over the whole surface. Okay, so step one. First we want to figure out what's the force per area. So to do that, we're going to take that total force P. So force per area is equal to P divided by the area of contact. The surface area of contact is pi times r outer squared minus r inner squared. And now we're going to figure out what the total normal force is for one of our little infinitesimal rings. So what's the increment of normal force for one shaded infinitesimal ring? Well, if this is the force per area, then dN is just going to be equal to this times the area in that infinitesimal ring. So dN is equal to P over pi times the quantity r outer squared minus r inner squared times, what's the area of this ring? It's the circumference times dr. So this is times 2 pi r dr. We can cancel those pi's, and we get 2 p R dr over R outer squared minus R inner squared. Now we want it, so now that's the total normal force that's applied on that infinitesimal ring. Now we want to use that to figure out what the total friction force is applied on that infinitesimal ring. So I'll call that D, force of friction. So D, force of friction, is just equal to the coefficient times D normal. What? R dr. This one? Where did we get that? We're eventually going to integrate over R. So eventually it's going to go away when we integrate. But for now, that dr just represents the infinitesimal thickness of this ring. So the total area of this ring is the circumference times the thickness. You can think of unclipping that ring at one point and straightening it out into a long rectangle. Okay, so now we're just multiplying on the coefficient, so this is equal to 2p mu R dr over R outer squared minus R inner squared. And then the last thing we have to do is figure out, well, no, there's really two more steps. The last step is we're going to integrate. But for this ring, now we're going to figure out what's the increment of moment that's applied by the friction on that ring. So what's dm for this ring? dm is just equal to R times the force of friction. And so that's equal to 2p mu R squared dr over R outer squared minus R inner squared. That's for one of those infinitesimal rings, so now we just have to integrate to get the total moment. So the total moment is equal to the integral from R inner to R outer of R df. And so I'm going to pull, well, I don't know why I wrote it like that. Just write it as dm. Okay, so I'm going to pull out all the constants. So out here we have 2p mu over the quantity R outer squared minus R inner squared times the integral R squared dr integrated from R inner to R outer. And so you get 2p mu over, when we integrate this, we're going to get R cubed over 3, so I'm going to pull the 3 out here. And then when we evaluate this integral, we're going to get R outer cubed minus r inner cubed. And that is as simple as you can make it. It's a little surprising. It looks like maybe you could factor stuff there, but you can't. Any questions about that thought process? Yep.
What equations are going to be given on the exam?
I'm not really giving, I'll give that belt friction one, but the other ones you need to be able to go through this derivation. And you can do it with numbers, so you're not going to have to do it algebraically, but you need to be able to follow that thought process. P is the force that's pushing those two things together. And so if you didn't have a hollow cylinder, if you had a solid cylinder, R inner would just be equal to 0. And you just integrate it from 0 to R outer. Okay, let me do an example. So let's say that we have a solid cylinder. There's a 10,000 Newton force pushing down. The radius of this cylinder is 0.1 meters. And let's say that this is at rest. What's the maximum couple that you could apply without initiating rotation? So let's say that the static coefficient of friction is 0.1 and the kinetic coefficient of friction is 0.06. Okay, so we're going to be looking at a ring like this with a thickness that's equal to dr. And a radius that's equal to r. And the distance to the outer edge is 0.1. Okay, so what's the first step? Yep, so first we want to figure out the force per area. So that's equal to 10,000 divided by 0.01 pi, and I'm going to keep that pi in there because there's going to be another pi coming up that'll cancel it. But if you want to just calculate that numerically, that's fine with me. So what does this give you? 1 times 10 to the 6 over pi, I think. What's the second step? Yep. So dn is equal to 1 times 10 to the 6 over pi times the area, which is 2 pi r dr. And so that the pi's cancel, and you get 1 times 10 to the 5, and there's that 2. So 2 times 10 to the 5 dr. Wait. That's that times, oh yeah, this is, I made a mistake here. So we're trying to figure out the total normal force acting on that infinitesimal ring. And that infinitesimal ring doesn't have the radius of 0.1, it has a radius of r. This has to be true for any general infinitesimal ring. So, so we have the force per area times 2 pi r dr. And so we get 2 times 10 to the 6 r dr. What's the next step? Friction. So dff is equal to mu times dn. Which coefficient do we want? Static, because this is at rest, and we're trying to find the boundary before rotation is initiated. So that was 0.1, right? Static coefficient of friction was 0.1. So this is equal to 0.1 times 2 times 10 to the 6 r dr, or 2 times 10 to the 5th r dr. What's the next step? dm, yeah. So dm is equal to r times dff. And so that's equal to 2 times 10 to the 5th r squared dr. And then the last step is just to integrate this over all the values of r. So m is equal to the integral from 0 to 0.1 of dm. So that's equal to 2 times 10 to the 5th times the integral from 0 to 0.1 of r squared dr. So 2 times 10 to the 5th times r cubed over 3 evaluated from 0 to 0.1, and I think you get about 40. Is that what you got? 40 Newton meters. Maybe I used a different number. Oh yeah, that's wrong. What do you get if you...
Like 67.
67? Okay, 66.7 Newton meters. 40 was if it was rotating and we were trying to figure out what it took to keep it in constant angular velocity. Okay, so if it's at rest and you apply a couple of anything up to this value, it'll stay at rest. If you apply a couple of anything greater than that, it'll, rotation will start. Any questions about that one?
What is the end?
Newton meters. Any answer? That's just the units of the couple. Yes.
Each kind?
I think one of each kind, yeah. And the problems on the test will be very similar to those.
So for the test, besides the belt one, which you said you'll give the equation for, you want us to go through these steps? You don't want us to just know
That's right.
the integral?
Yeah, that's right. Any other questions? Any other questions about the test or anything? Okay.
Can you scroll up a little bit?
Yeah.